So let's start off this session with Harsh Patil from the University of Bristol, who will be talking about coarse separation of metric spaces. Over to you.
Thank you, Juma, and thank you, organizers, for inviting me and giving me this chance. Okay, so let me start off by just uh, talking about notation that I've set up. So n sub r of A for a subset of a metric space A will just be the R neighborhood of A. So it'll be all the points in X that are at distance less than or equal to R from the set A, from the subset A, right? Okay. And today I'm going to talk about coarse separation. So you can think of coarse separation as an analog of separation in a topological space. So separation means that if you have a subset of a topological space which when you delete it, if it disconnects the topological space. So if x minus a is not a path connected space, you say that a disconnects or a separates x. And we're going to discuss an analog of this in the space in the world of metric spaces. Okay, so let X be a metric space and A be a subset of it. We say that A coarsely separates X if there exists a subset C such that neither C nor X minus C is contained in some finite neighborhood of A. So for any R, neither C nor X minus C are contained in NR of A. And for every r greater than 0, there exists r prime greater than 0 such that the r neighborhood of C intersection with r neighborhood of x minus C is contained in the r prime neighborhood of A, right? So if your metric space is one connected, right? So if it's one connected, which means that given any 2 points x and y, you can take there exists a sequence of points such that distance between subsequent points is less than or equal to 1. And yeah, basically you can go from x to y by taking jumps of length 1 or less. Then you just need this constant r to exist. So this constant r prime to exist for r is equal to 1, right? Because if it exists for r is equal to 1, then you can prove that it exists for all r, right? Okay, let me give some motivation for why this for this definition. Okay, so suppose that G is a finitely generated group and it acts on a tree without global fixed points. So think think of a Bassett tree if you like, and so we are really working with a splitting of a group of this group G, and let E be an edge and edge be and the subgroup edge be a stabilizer of this edge, right? And if this happens, then edge coarsely separates G. So we are thinking of G as a metric space equivalent with some word metric, and edge as a subspace will coarsely separate it. Okay, and this becomes clear if you think about the orbit map from G to this tree, right? So you fix a point P and you take this orbit map. G goes to 0 P. Then what happens is that F is actually an L Lipschitz map for some L. And what you're looking at is, so when you're looking at edge, so you have this group G, which is a metric space, and your subgroup edge maps to this point P, or this right? And so now deleting this edge disconnects the tree into two parts, and the pre-image of that we will call C, and its complement will be the pre-image of the lower half of this tree, right? And so if you want to go from this upper half, or from C to X minus C, then then you look at a path which joins these 2 points, and you project that path onto the tree, then it will give you a path between a point in the upper half of the tree to the lower half, and this path has to then pass through this edge necessarily, and therefore the original path that you are looking at in the group G uh, has to necessarily pass through the subgroup edge, right? So this is the motivation for coarse separation. And so if you are able to better understand which subsets coarsely separate your metric space, then maybe you can say something about splittings of group. You can maybe give some sort of an obstruction for a group splitting along a certain subgroup, right? Okay, and now I would like to go on a bit of a tangent and introduce asymptotic dimension. Okay, so it's a notion of, it's an analog of topological dimension, of Lebesgue covering dimension, but one which makes sense for metric spaces in the large scale geometry sense, right? So let X be a metric space. We say that the asymptotic dimension of X is less than or equal to n if for all lambda greater than 0, there exists a cover of X such that there is a uniform bound on the diameters of sets in this cover U, and that the Lebesgue number of this cover is greater than lambda. So what do I mean by that? So the Lebesgue number of a cover is the number such that any set of diameter less than or equal to lambda is contained in one of the sets in this cover, right? So if this happens, and such that, so the Lebesgue number is greater than lambda and the multiplicity is less than or equal to n plus 1. So by multiplicity, I mean that every point is contained in at most n plus 1 sets in this cover. So if this happens for every lambda, then you say that the asymptotic dimension of your space is less than or equal to n. And if this statement, asymptotic dimension less than or equal to n, is true for n, but if it's not true for n minus 1, then you say that the asymptotic dimension of your space is exactly n, right? So here is an example. We're looking at the real line, and the asymptotic dimension of the real line is actually exactly 1, but we're just gonna show here that it is less than or equal to 1. So we are looking at, so given lambda, we cover the real line with intervals of length 5 lambda, such that adjacent intervals overlap in a segment of length 2 lambda, right? And so yeah, and that can easily be achieved. So one can confirm that this cover has Lebesgue number lambda, because if you pick any point and draw the ball of radius lambda around it, then it will be contained in at least it will be totally contained inside one of these intervals. Okay, so this is how you show that the asymptotic dimension of the real line is less than or equal to 1. And in general, asymptotic dimension of Rn is exactly n. And so the picture for R2 looks like this, right? So there are blue, red, and green bounded sets here, and every point is contained in exactly one in at most one blue set, at most one green set, and at most one red set. So the multiplicity of this cover is exactly 3, and it consists of bounded sets, and the one can control the Lebesgue number of this covering by just dilating it, right? So to control the Lebesgue number, we just need these threefold intersections that we have to be big enough, right? So that's the sort of idea behind why the asymptotic dimension of R2 is 2, or yeah, right? And asymptotic dimension is a quasi-isometry invariant. So if two metric spaces are quasi-isometric, they have the same asymptotic dimension, right? And okay, so the next thing I want to introduce is another quasi-isometry invariant. It's a cohomology theory, but but there's no need to be scared by this, because I mean, the definition is fairly straightforward, right? Okay, so let X be a metric space, and X, we say that we denote X to the power n by we denote the n-fold product of X by X to the power n, right? So these for us will play the role of n simplices in our cohomology theory. And so we take the most basic basic co-chain complex that we can form out of this. So it's just the set of all functions from x n plus 1 to z. That is our nth chain group. And there's a natural co-chain map going from Cn minus 1 to Cn, which is given by, yeah, F goes to F composed delta. So here delta is the usual boundary map that you have, where, yeah, you take alternating sum of faces, right? And yeah, you get a chain complex out of this, but it's an acyclic complex. Nothing interesting is happening here. Homology of or cohomology at any particular index will be trivial here, right? But and as you can see, we have not made, even if X is a metric space, we have not made use of its metric structure here. So that's kind of that's to be expected, right? So now we consider a subcomplex of this. Right? We only consider the functions from xn plus 1 to z, such that for all r greater than 0, there exists two things: r prime greater than 0, so a constant, and a point y, such that if there is some simplex which is in the support of f, so by that I mean f of sigma is not equal to 0, then these points x0, x1 up to xn, they all lie in a ball of radius r prime. Okay, and so this is where the metric structure of X is coming into play, and it is a subcomplex of C star X, and now the cohomology of this may not necessarily be trivial, right? And so we denote the kth cohomology of this complex by Hx superscript k, and we call it the coarse cohomology of X. Okay, and similarly, there is a dual theory, a dual to this. It's a homology theory. So here, instead of considering functions, we are thinking of formal sums of this form, and they're not necessarily finite formal sums. But yeah, so sigma again here, sigma is a n+1 tuple of points in X, and C sub sigma is just a coefficient. It's an integer, right? And we're looking at, so again, this is a acyclic complex, but now we look at a subcomplex of it, and it gives us a, like, we impose two conditions on it. We say that for any bounded set B of X, only finitely many simplices have a vertex in B. So it's a local finiteness condition. And another condition that we impose on our formal sums is that for every for a given alpha, for a formal sum alpha, there exists a constant C such that every simplex that is in the support of alpha has diameter less than or equal to C, right? So and again, we get a now in this particular case, we get a chain complex rather than a cochain complex, and the cohomology of this complex, we call it the coarse homology of X. Yes, okay. And now I would like to introduce coarse PDN spaces. So coarse PDN spaces are analogs um of open manifolds in the topological category. So they are the metric spaces that uh, sort of follow, that have the same large scale geometric properties that open manifolds have, right? So I'm not so the definition is a bit technical, and I'm not going into too much detail, and we don't actually really need it for the sequel. But yeah, so the definition is stated in terms of these chain complexes and cochain complexes, and the existence of certain chain maps between them, which are chain homotopic to identity, and they sort of respect the metric structure and so on. But I'm not gonna go into detail here, into too much detail here, right? Examples here, examples of coarse PDN spaces are actually, if you have a compact aspherical n manifold, such as the torus, then its universal cover is a coarse PDN space. So you think of the metric of the universal cover coming from the from X. You have some triangulation on X, and you're lifting that triangulation to X tilde, and that gives you a metric on X tilde by just, if you just restrict it to the to the one skeleton of X tilde. See, yes, okay. Oh, sorry. Okay, and so now, right, okay, so I think I skipped something. Sorry, I see. Okay. Yeah, okay. I think I skipped something. So let me just write that down here. Um, there was, so recently, there was a result by Panagiot, by Seleucides. It said that if let G be a finally generated group, such that asymptotic dimension of G is equal to n, then there exists a subset of G such that A coarsely separates G, and asymptotic dimension of A is strictly less than n. Okay, and there was a conjecture as well which said that if a subset A of Rn coarsely separates Rn, then asymptotic, sorry, dimension of A is greater than or equal to n minus 1, right? So any hyperplane in Rn will coarsely separate it, right? And it'll have asymptotic dimension n minus 1. But the conjecture stated that anything that has that has dimension lesser than that cannot coarsely separate Rn, right? And this was this is the motivation for me. This was what got me interested in uh, this particular collection of ideas, right? So right, so okay, so why right, Rn is a coarse PDM space, so so this is the right setting if you're thinking about Rn or edge n, the upper half space of dimension n. Right, so there's a theorem by Banerjee and Okun which says that if X is a coarse PDN space, then the kth coarse cohomology of X minus A is isomorphic to the n minus kth coarse homology of A. So it's a, and here we are thinking of X minus A as a pseudometric space. So X minus A, we are thinking it of, so on X minus A, we have this following metric. We have the metric D of A, XY, such that it is minimum of distance X, Y, and distance of X to A plus distance of Y to A. Oh, I think I should maybe write it somewhere else. Okay, so we have sort of coned off A. We think of any 2 points in A as being at distance 0. And this gives us a pseudometric space. So even 2 points which are distinct can have distance 0 between them, right? And so like we can define coarse cohomology and all of these things for a pseudometric space. And yeah, so and another observation by Banerjee and Okun is that edge X, so the first cohomology of this complement is non-trivial if and only if A separates X, right? And so if you're thinking of, so this proposition applies to all metric spaces, not just coarse PDN spaces. But yeah, but combined, if you combine the two, it means that if a subset A of a coarse PDN space X separates it, then you get that the n-1th coarse homology is non-trivial, right? And so if you want to then prove this conjecture using these two things, then we need to show that non-vanishing of non-vanishing of homology in a certain dimension will give you a lower bound for your asymptotic dimension, because yes, because you have non-vanishing in the n-1 dimension, then yeah, if you are able to prove that that this following theorem is true, then we have a result, right? Okay. So now I'm going to share a bit more about how you can go about proving this theorem.
Harsh, sorry to interrupt. It's just to let you know you've got about 4 minutes left before we need to move on.
I see.
Oh,
I see. Okay, no worries.
yeah, carry on. Sorry.
Yes. Okay. And so, well, to compute coarse homology, we can use. So I'm gonna tell you a technique of computing coarse homology, and so I'm gonna introduce something called as anti-check system. So it is a sequence of covers of your space X, such that each cover is uniformly bounded, but the bounds on those covers tend to infinity. So yeah, so and all of these covers are the so-called good covers. So it means that any point is in only finitely many sets in this cover, right? Um, so a sequence of good covers is said to be an anti-check system if there exists a sequence of real numbers that tends to infinity, and says that Rn is a bound on the diameters of sets in Un, and it is also a lower bound for the Lebesgue number of Un plus 1. So what this means is that every set U in Un is contained in some set in Un plus 1, right? So Un is a refinement of Un plus 1. Right. So now I'm going to introduce nerves. So given a cover, you can associate a simply shell complex to that cover by taking the zero skeleton of this simply shell complex to just be the set of just to be the cover, and then an n+1 tuple of sets in this cover spans an n simplex if and only if the n+1 fold, like the intersection of all of them is non-trivial, right? So here you can see that there are 3 sets. So corresponding to them, we have 3 vertices, and they pairwise all of them intersect. So we have edges between all 3 of them, but there's no point. But the threefold intersection is non-empty, so we don't have a 2 simplex. Yeah, we just have a triangle, right? And but here below we have a threefold intersection, so we get a full 2 simplex here, right? So yes, so right. So when we have such a anti-check system, what happens is that U1 is a refinement of U2, is a refinement of U3, and so on. Right. So yeah, I think I've said what a refinement is, but yeah. So correspondingly, on the corresponding nerves, you get simply shell maps. So there's a map from n of u1 to nu2 to nu3, so on. So it's the natural map that you can think of. Every vertex in u1 in n of u1 corresponds to a set in u1, and it's contained in some set in u2, and you send those vertices via this map to the corresponding vertex in nu2, right? And there's actually in some cases there can be an ambiguity, but this ambiguity is bounded. Like you can choose any one of those. Like it might happen that some set is contained in some set in u1 is contained in two different sets in u2, but you can send the corresponding vertex to any one of those, right? You get a sequence of uh, simply shell complexes and simply shell maps between them, right? And am I how am I doing on time? Do I
I'm
have
afraid
time?
you're actually over time, so
Oh,
if you could
I
try
should
and wrap
stop.
up.
Yeah. Okay, I'm just gonna stop now.
Okay, great. Let's thank Harsh for their talk. We'll maybe just do one very quick question.
Harsh, what is the final result that you have, like, what is the final theorem you wanted to prove?
Oh, I wanted to, right. So the final result was that if you have a coarse PDN space X of dimension n, then a subset of dimension, if a subset coarsely separates it, then it has dimension at least n minus 1, asymptotic dimension at least n minus 1.
Nice. All right.
Okay, let's thank our speaker one last time. Thanks, Harsh.